When developing statewide standards in education, we as a state have to really ask some important questions. So let's imagine a fictional conversation where this is going on, where we ask, what's the purpose of science education? Well, the answer when we were developing the California Next Generation Science Standards was a very clear answer. It's to prepare future citizens and future scientists. Of course, as educators, we need to start asking the question, well, what do we need in order to do that? And how are we going to accomplish that? Well, at the statewide policy level, the answer was a resounding all standards for all students. So what exactly does that mean? Well, students need all the pieces of the puzzle to understand and address the world's problems. If they're missing one piece, they may not be able to get the whole picture and may not be able to develop effective solutions. In California, there's also another important aspect, which is that we feel that all students should have equal access to the tools of science and engineering. It's not equitable if different populations are getting access to different pieces of information in different parts of the science curriculum. Well, that's all great, but now as educators, we need to figure out, now that we've got these standards, how do you fit all these standards into the high school curriculum? And the way that California has developed this, they've given us a bunch of different options. Districts and individual schools are going to be able to choose how to do things in high school. The framework for science proposes 3 different possible models, one called Every Science Every Year, one called the 3-course model, one called the 4-course model, or districts and schools can develop any model they want of their own. California does not mandate any particular sequence. So what you see in the framework, these are some examples of how you could do things. Let's take a look at those in more detail. They range based upon the degree of integration of different science disciplines. And the different colors here represent the different courses that you can see: physics in orange, chemistry in red, biology in blue, biology in green, and earth and space science in blue. Now, those are the disciplinary content of the courses. So let's take a look at the earth science every year. Let's take a look at these models in more detail. There are 3 models proposed in the framework, and they're illustrated here with these diagrams. The different colors represent different disciplinary core ideas within different fields. The yellowish-orange for physics, the red for chemistry, green for the life of biology, and blue for the water of the earth and space science. And they differ in the degree of integration between these different disciplines of science. Let's focus in on a few of them. With the Every Science Every Year 3-year model, this idea is that we address the simplest phenomenon in year 1 and build developmentally from there, looking at more and more sophisticated phenomena in later years. And we're addressing phenomena from a fully interdisciplinary perspective, looking at the different disciplines of science as we need them to answer questions about specific scientific situations. And it's an absolutely wonderful idea. But with phenomena, they should be locally relevant, and it was really hard as we were putting together the framework to produce an example course that would be interesting statewide. And so what happened was that this great idea and principle model was relegated to an appendix in the California NGSS framework. It doesn't mean that it's not as good, but it means that individual districts, if they're interested in this pathway, are going to have to pave the way for themselves to make something that really is meaningful to their teachers and their students. At the other end of the integration spectrum is the discipline-specific 4-course model, where there are 4 different years of science, each devoted to one discipline of science. Now, the order of the courses is not prescribed, so what I'm showing here is just an illustration, and this is closest to the status quo in terms of the course titles, but there are some important changes here that this exposes more students to more sciences. And so you can see the graph in this area shows the current distribution of enrollment in California in science content courses and what we'd have to have in the future if we had the 4-course model going on here. We'd need to change the distribution of who's taking what, and more people would be taking courses. And then, of course, even though these course titles sound very similar, the actual content and approach needs to reflect the three-dimensionality of the next generation science standards. So there's somewhat of a compromise, if you will, here in between these two. The Earth Science Integration, the three-course model, where we created 3 new example courses where Earth and space science phenomena motivate the study of other disciplines. Now let's look at the titles of these courses. They're the Physics in the Universe, Chemistry of the Earth System, and The Living Earth. Now these titles are not a mistake. They're not an accident. They're not simply called Physics with Earth Science embedded, or Chemistry and Earth Science. It's about an integration between these two, and they really should not be treated as biology, chemistry, and physics with Earth and space science sprinkled in. We're trying to use Earth science phenomena to motivate and excite our students about these other aspects of science. And again, in this example course sequence, the order of the courses is not prescribed by the state at all, and the framework chapters were written basically with to be sequence agnostic, meaning you could develop them however you wanted. There are separate videos that go through the conceptual flow of each one of these courses, but the 3-course Living Earth model looks like this, looking at a range of topics. The Physics in the Universe course has a variety of different phenomena that are scattered about and unified through the idea of alternative energy. And the Chemistry in the Earth System has a common theme looking at CO2 that ties together many different aspects of the Earth system and chemical systems. As you're looking at all of these, you might be asking the question, well, does the sequence matter? They were written to be sequence agnostic, but is there a better sequence than one way or the other? And of course, in the 3-course model, there are 6 possible permutations, and each can be driven by different philosophies. Some of the well-known philosophies out there are the concept of physics first, there's Earth Science capstone courses, there's the biology as a gateway as a principle, and the bottom line from my personal perspective is that all disciplines can be taught with different degrees of rigor in a developmental sequence. The important thing is you look at your school and your district and what your strengths are and what your focus you'd like it to be. What would you like to be building towards? What are the most sophisticated problems that are interesting to your community that you're in? And be building towards those and coming up with whatever sequence you want. So I know that a lot of people are going to be fretting over which sequence to do, but in the grand scheme of things, any one of those sequences could be a wonderful implementation. It really doesn't matter what you choose for the sequence. It matters how you actually do it and making sure that you are doing it in a developmental progression where ideas build on one another instead of simply just having things go 1, 2, and 3. So good luck with your decisions about which model of science to do in high school, and hopefully the framework chapters that we've written will give you some good ideas and inspiration.